theoretically solve it, but nobody does. Because it's so hard to solve when you have all three things present. So what people usually try to do is get rid of some. Get rid of migration. If you're looking at neutral species, that's pretty easy. They'll get rid of, usually the one they try and end up with is diffusion. They'll get rid of convection, or they'll use it at the same rate that it kind of falls at, and it ends up being that diffusion layer is the thing that maximizes it. So if you really had to solve this equation, for how fast your stuff is going to get to your electrode, again, this is the I over NFA, kind of thing, how fast it's going to get there with all those equations, it would be really hard to do. And so, but that's the equation. I don't know if that was in the French or not, it probably is. It was in chapter 1 too. We skipped it. I told you, if you just memorize chapter 1, you could do it. All right, so that's the non-sequence equation. One thing to say about migration. I'm not going to cover it too much. You have to think about migration of all charged species, right? And so if you have a lot of electrolyte, right, for the most part, that's going to undergo migration. That most of the charge balance through the electric field, right, is going to be electrolyte moving and not your sample. So you do have to kind of think about that. This is one of the reasons that they often ignore migration. They say, oh, well, my actual molecule that I care about, J, isn't really, carrying much of the charge, that most of what's moving, is going to be electrolyte. And so people don't think about it quite as much. It is possible, however, again, they kind of think about, in the book they give these examples, and they're like, what if you have copper 2+, and you apply a negative voltage to your electrode, right? Well, as long as there's nothing there, it's diffusional sort of current due to it wanting to diffuse would be in that direction. And because this is negative and that's positive, right, the migration would also want to be in that direction. So you get current due to mass transfer for both. But it'd be possible, instead of using copper, to look at something that was negatively charged. Right, so now if I apply that same negative voltage, it might want to diffuse that way, right? But its direction of migration would be pulling it the other way. And so, in reality, though, as I said, the way to get around all of these things is just to add a lot of electrolyte. And again, that tends to minimize any of the problems with migration. So we won't talk much more about migration, although they go through it, I think, in greater detail in the book. And if you're a separations person, you should think about it probably a little bit more. Well, this is electrochemistry class. I hope if anyone, Shannon's working on electrochemistry separations projects, other people might access too. There's a lot of good stuff in separations. Again, kinetics, thermodynamics, diffusion. Doesn't really matter which experiment you're doing, they're the same. So hopefully this is good for that kind of stuff too, even if we don't do that. Okay, so most of the time then we're going to go and talk about diffusion. Let's talk diffusion. Okay, so again, it's generally assumed to be the rate limiting step in most electrochemical experiments. And so, again, if you ever learn anywhere about diffusion, not just here, normally the main model for diffusion is generally considered to be a random walk, where you have some sort of step size, right? And you know, each time you can take a step. You can either go forwards or you can go backwards. You know, and on average, how far, if I let you take, 500 steps on average, how far away from the start would you get, kind of thing. It's a probability model. And so, if you were to solve that, you get out this is called the mean square displacement again. So it's like how far you would get, but squared. We're just going to call this in a minute. But this is oh, sorry. That's the answer. This is the number of steps, turns out, times the length of a step, squared. And again, that's not really useful to us. We'll take a probability class and go ahead and there. For our purposes, analytical chemistry, turns out that the number of steps times the length is equal to 2 dt. So 2 times the diffusion coefficient times how long you were allowed to go, as far as that goes. So this leads us to an equation everybody should have memorized, and that is this. That the approximate distance you could go, so as I said, we'll use d for distance, is equal to the square root of 2 dt. So that is how far you can go in a given amount of time, approximately. So, I mean, this comes out all the time because people think you have this memorized. And again, it's not that you necessarily have always done the calculation, but for instance, if you're in microfluidics, we'll give an example. And you have a 30 micron channel, and people say, well, there's no mixing. Well, I mean, if you sat there forever, there would be. So then you have to kind of say, well, how long would it take to actually mix if it had to go 15 microns? And the equation you want to pull out is nothing fancy, it's just the square root of 2 dt. Okay, so if you have to guess d, what's d? What's d for different? Let's take an order of magnitude, 10 to the minus, I'll even help you out. 10 to the minus what? Any diffusion coefficient of any molecule. All right, now I got the other side of it. Because we've done a great job bracketing. All right, 6. Yeah, there we go. The diffusion coefficient of dopamine in a beaker is 6 times 10 to the 6. Now I'm going to get the units right. It's always in centimeters. Well, distance is in centimeters. This is in time. Right? And so, yeah, centimeters. Yeah, that's fine. That's right. See, I can do math. All right, so centimeters squared per second. That's in a beaker, and then the brain is this. I highly recommend, since nobody seemed to know a diffusion coefficient today, that does not continue for any exam you ever take here. Because again, people say, what's the order of magnitude? And I tell people, when I taught separations, I said, just guess 10 to the minus 6. I was like, you can't be wrong. If it's a protein or something, it might be like 10 to the minus 7th, or it might be 10 to the minus 5th. But you're not going to be more than one order of magnitude off for any molecule known to man if you guess 10 to the minus 6th. And the professors were like, they'd just be like, oh yeah, I would have thought 10 to the minus 7th, and they could go on, right? But if you guess 10 to the 3rd or something, you're going to have problems. So you're not going to be more than 1 order of magnitude off. I promise you. Every diffusion coefficient is between 10 to the minus 5 and 10 to the minus 7. Just guess 10 to the minus 6, you never even know. And if we have to do real diffusion modeling, we'll get more specific than that. But that you need to have some idea of what you're going with. All diffusion coefficients are always in centimeters. Again, it's not in the Euclid to know a number about that. Okay, so we've again learned Dr. Renton's favorite diffusion coefficient. Yes, I ask people to solve this at their orals all the time. It's not that hard. You should be able, kind of back of the envelope, to pull out a diffusion coefficient for something and figure out, well, how long would it take something to get to your electrode right in the brain? This is back of the envelope. There's much. Again, you can write random walk models, which we've done. To model this kind of stuff, you can do it back of the envelope pretty quickly as well. Okay, so we get about diffusion without talking Fick's laws. Hopefully you were wondering where they're coming. And so these are differential equations, basically, that describe the concentrations in terms of time and position. So we're going to have, again, we're going to learn about concentration as a function of time and distance from the electrode, x. So again, we kind of learned about this one's already. So Fick's first law says that minus j of any given point of x and t, again, a distance variable and time variable, is going to be equal to diffusion coefficient times the gradient in concentration. So I solved this a little earlier when we did the delta thing, right? So that was Fick's first law, which we're getting back to that. All right. And then again, that's all just I is equal to NRK kind of thing. The second law, and I'm pretty sure the book probably derived these, and I don't choose to today. The second law is the one that tells you about the flux as a change in sort of distance. So this one is the second order differential equation. So the change in concentration of O of x dt. So how it changes in time is a function of the second derivative with respect to distance. These are all these are not twos, right? They're the partial derivative. What are they? Still like the d kind of partial derivative. Instead of, should just put them as d's. The little d's for partial derivatives. All right, so again, now most of you are not math lovers, probably don't sit around in your sleep solving, differential equations all that often. And so you can theoretically always relate concentration to distance and all of that, but practically it's not always the easiest to be able to look at these. Right, so let's think for a second. Well, again, this is capable of probably just 10 pages, and we're kind of condensed just a little bit. So one of the things I think is helpful to think of, though, is kind of a diagram that looks like this. So let's say this is x, and over here, this is x plus dx, meaning we've gone some distance dx from there. So we start at 0, and we go to 2, so right, dx is 2, or something like that. We want to know what's the flux at this point in time. What's the flux in? So the flux of O here at this given point. And then we want to know what's the flux out. So at x plus dx, what's the flux out, right? So I have, I mean, if this was like a box or something, how many things came in versus how many went out. I just brought an example of like a store with customers. How many came in the door versus how many went out the back door, kind of thing, right? And that tells you how many things are in the middle, right? And we know the rate something's coming in and the rate something's leaving. Tells you something about the amount of people in the middle. And so it turns out that again kind of gets you back here, that the rate that concentration changes over time is equal to the flux that came into that little box minus the flux that came out over X. So as far as that goes. So again, I think this may be a little bit better way to think about than second derivative. But that flow should just go ahead and solve this for me. But I like pictures that explain to me diffusion. I think this picture explains to me diffusion pretty well. How fast things can come in, right? How fast things can come out, kind of relates them back. And so up until this point, we've kind of we've assumed that all diffusion is just linear. Things are just kind of linearly flowing. Turns out that that's not really the case. Right, so all of this is assuming that you have basically a flat, long electron. And if you had a flat, big electrode, then you would get linear diffusion. But we don't love flat, long electrodes in that lab, right? So we need to learn some other geometries, unfortunately. Or maybe fortunately. So, let's look at the disk. So let's just assume that our disk electrode is the end of that. So if you think about diffusion, you say, well, right, diamond things are going to diffuse in that way. That looks pretty linear to me. But it turns out if you have a fairly small radius disk, that if you look over here, what if a molecule is over here? Do you think that molecule could get to the electrode? Yeah, and if a molecule is over here, could that molecule get to the electrode? Yeah, right, and so what it's really, kind of sampling from is more of a sphere, like a hemisphere, right? Rather than just, it had to be up here and to reach the electrode, it had to be straight up, right? Because it's going to end up sampling from the sides, right? Even some things that are down here might be able to diffuse up and over, right? I mean, not everything goes in a straight line. And so the signal that you get is larger than if it was just linear diffusion. So you say, well, what's the difference? What matters here? How do I know? Again, for this long electrode, that's why I'm saying that the diffusion distance is going to be sort of small compared to the radius of your electrode. So you want to know, how do I know if my electrode's big and follows this rule or small? And here the diffusion distance is not going to be so big compared to the radius. So the smaller you shrink that, the more, as I said, it matters then radially what happens. And so it turns out that you can write out, which I think I'm not going to do. You can look in the textbook if you want to be like the whole thing. You can solve this analytically, so go to it. You can solve it analytically, and it's really nice because you can solve it analytically and it does not depend on time. So you can you can do math and solve plus transforms. That's why I'm going to write them down for you. Of how to solve it. But what I want you to know, again, you notice I'm de-emphasizing the math and trying to emphasize the concept of you're going to get more stuff to the electrode at a disk than just the stuff that was kind of above it. But it's going to sample from the sides as well. Okay, so now that we've done the disk, let's do a cylinder. Right, so now I have a cylinder. Look, I'm holding one right here. right? So now I have stuff, right, that's going to come from all sides. So in some ways it's not different than maybe having a sphere. We're going to leave out sphere. The electrochemist will solve that too. Or hemisphere, there's a lot of hemispheres, kind of thing. So, but the thing about now, we're not just in linear coordinates, we're actually in what they call spherical coordinates. So, right, if I were to look at, this electrode, if I were to go out some radius around it, right, and then I would kind of like put my finger around in a sphere, right, all those points would be the same distance, right? I would be the same distance away. So as I go out, my sphere gets bigger. So that's why they call it spherical coordinates. So instead of, this is like a line, and as I go out, I'm linear away. Now it's like you have to think of it as spheres getting bigger. So that's where they get the spherical coordinates from. But here's the problem. When I first sample, I might deplete, again, what would be a sphere around there. And as I sample longer and longer and longer, right, the sphere I do gets further and further away. And so, the sphere of stuff that would be depleted, if I just were to apply positive potential and there was dopamine in the six, and I'm not scanning or anything, right? How much stuff is going to be there? Well, I'm going to deplete what's right at the electrode, right? And as time goes on, the depletion area is going to grow out in spherical coordinates now, right? Those spheres that there's no dopamine are just going to get bigger and bigger and bigger. And so it turns out that you can't solve this analytically. And so it turns out that this is always dependent on time. D, sort of the diffusion length. Whereas with the disk, it turns out you can solve it. And it's not dependent on time with the cylinder. So people don't like cylinders. If you're going to do a fundamental study of diffusion to your electrode, you should never pick a cylinder, you should always pick a disk. It just ends up being easier to solve. You want to know why people start with disk electrodes? It's probably because, again, the fundamentals are much easier to look at as far as that goes.